I had no idea. Yeah, I was always out with doing my.
Okay, no, he's got it. Okay, we're good. My name is probably.
Let's continue with our calculator. That's review time. They equals.
You don't know what put down. You're not. You're not. You're growing.
Okay, I think we got through a portion of page 2. Let's continue going though. We know that with extreme value theorem, we're only pulling information from the sine line, so we only care about endpoints and vertical points. But because we're looking for absolute minimum, all we need is relative minimum, and those are the only places that we can get an absolute minimum. So you also want to find G of 4. So G of 4, let's see, we found relative minimum. G of 4, we're just going to total up all the information from our graph. And if we're looking at all the values here, we got a rectangle minus a semicircle, so that's going to be 2 minus 5/2. We add all those values up. Compare those y values, and we see that this is around 5 versus -1 versus 0. The lowest y value amongst these three is -1. So we can say absolute minimum value is negative.
Yeah, so we only plug in like pointers or endpoints.
Endpoints, yeah.
Okay.
So EVT, we do endpoints and critical points,
Okay.
but we did not test 1 or 3 because 1 is not a relative max, relative min. And then 3 is a relative max, and relative max we didn't need to test that for absolute. But if you tested 3, it's not wrong. It's just an extra thing to do. Number 4, find all the values where the graph has a point of inflection. So again, if you're looking at what we call the G prime or the derivative graph, then we know that the peaks and valleys of your G prime graph will be your points of inflection, right? So -3, 1, and 2. Okay. And we're just going to practice through all the various types in this packet. So today I'd like to be able for us to get through problems. Let's try page 5 and page 6. And if we have time, we'll come back and we'll do another one with derivative graph. So let's do page 5, page 6, and page 3. Okay, table below shows the speed of a sprinter at time intervals in seconds in a 200-meter race. So at time 0, starting velocity is 5 meters per second. And then we see him potentially top out his speed at 11 seconds, 9 meters per second. And then he slows down. Now, we don't know that's the maximum, but that's based off of the values that we have, that's going to be our best estimation. But I just want to kind of give you an idea that these represent speed, doesn't represent distance here. So it says estimate the depth integral from 0 to 20 of integral of v of t using the following methods. Okay. So first off, though, what does this represent? Integral of v of t. Distance, right? Or how about this? Change in distance. Because we know that using first theorem, integral of v of t is just x of 20 minus x of 0. So that really tells us is that this x of 20 will tell us how much distance he's covered. And then this is how much distance he's covered at 0 seconds. So if we subtract these two, we figure out how much change in distance or displacement, right? Displacement. So if we take the integral here, what's going to happen with our units? Our units will also change. Meters per second will turn into what? Meters, right? So think about this. This is integral. Integral is multiplication, is area. Area means multiplying your two units as well. So whenever there's integral notation involved, your units will never stay the same, okay? Meters per second times second is just meters. Okay, so we're going to do trapezoids here. So we're going to basically figure out how much distance he covers in those 20 seconds, right? Okay, it doesn't mean that he ends his race here. It just tells us how much, where he is 20 seconds in, or how much speed he's covering 20 seconds in. Okay, so 6 trapezoids. Our area, remember, for trapezoid is 1/2 width, height 1 plus height 2. 6 trapezoids, so we want to be able to split these intervals into 6 subintervals. Remember, when you do subintervals, you're always going from the middle of one order pair to the middle of the second order pair. So, and they're always going to overlap. Hopefully we can get to 6 here. 3, 4, 5, 6. Thanks. So that's 1 subinterval, 2 subinterval, 3rd, 4th, 5th, 6th. Okay, so we're to split up into 6 subintervals, each covering the same number of order pairs. It doesn't mean that the width is the same, just the same number of order pairs. Okay, so we just have to just go through each of these areas here. So the width for my first trapezoid is what? 2, right? 2 minus 0 is just 2. And then height 1 plus height 2. Now, just make sure that even if this subinterval spans across more than 2 or 3, your every area for each trapezoid is only 2 heights, right? You're not going to add up all the heights. You're just going to take the heights at the end of your subinterval. Okay. Okay, it's a little tedious here. On the test, I won't make you do as many as this, but okay, so just to save you time to have to, rather than have to add all this up, I'll just tell you that adds up to be 155.5 meters, but Just make sure you know how to arrive at these numeric values from your table values. Part B, we want 3 left-handed rectangles for the entire interval from 0 to 20. So I'm going to do another, let's see here. Maybe I can go first 3, second 3, and third 3. So first subinterval, second subinterval, third subinterval. So every subinterval, they may not have the same width, but they will all span across the same number of order pairs. Okay, left-handed rectangles. Okay. What's the width of my first subinterval? 5 minus 0. You just look at the first row.
Yeah, how do you know how much like interval to look on the top, like all those brackets? How do you know how much?
Yeah, you're gonna have to kind of play around. Kind of play around and see that when it spans from beginning to end, how can I create however many subintervals and spans across the same number of order pairs. Just a little bit of trial and error, but it won't take long.
Because it'll be short on the seats.
Yeah, I probably won't give you like 6, be like 3 or 4.
Okay.
Okay, what's the height of my first subinterval? Yep, this is left. If it's right-handed rectangles, you choose a 7. If it's a middle rectangle, then you choose the 6.5. Second subinterval has a width of 6, a height of 7. Third subinterval has a width of 9 and a height of 9.
The widths for the subintervals, like, they don't need to be the same, right?
They most likely will not be the same. Chances are there won't be the same. AP exam as well. I mean, if they're the same, it's great, but we want to prepare for them not being the same. Okay. 3 right-handed rectangles. So still spans across the same subintervals. So all our width we can just carry down. It's just a different height value that we're pulling. The first rectangle will have a height of 7. Second will be 9. The third will be 7.5. So the hope is that when you see a Riemann sums problem where there's a table of values, it feels like it's a problem that you want to see on the AP exam because it just feels easy, right? It should feel like an easy as far as pulling the areas. Okay, 3 middle rectangles. Okay, so if you're having trouble identifying the width and height or subintervals, let me know. I want this to be an easy process for you guys, especially compared to, well, I mean, these are all not too bad, right? But this one is the easiest of the 3. Okay, everybody good here? Find the average velocity. So average velocity. So think in terms of, well, I have a average value theorem. I can adapt average value and make it average velocity.
You're only giving the velocity function, then like, why do you need to find the integral? It's saying average velocity, right? It's not. It should.
Yeah, average velocity. So we can say, well, if average value is the integral from a to b of f of x or 1 over b minus a, then can I say the average velocity It's just 1 over b minus a integral from a to b of v of t dt. Right, we accumulate all the velocities, we get position, change in position over the change in time will give us velocity, right? So it says using the 6 trapezoids. So I can replace this with what? Yeah, the trapezoid approximations, right? 155.5.
So like on the test, do you want to keep our answer exact or like approximated places?
Yeah, 3 decimal places is the standard. I do want to draw a nice connection here between what we've done before with particle motion versus this. Do you remember how before I said, oh, if you do average velocity, you're just doing slope, you're not doing any calculus? So it depends on where you're coming from, right? So let's say I asked you for average velocity for something for a position function that is, let's say this. Right, so this one we don't do calculus, right? Because average velocity is just change in position over change in time. So my average velocity is simply x of b minus x of a over b minus a, right? But then now we're doing average velocity where I'm giving you the velocity function. So I told you now that your average velocity is 1 over b minus a integral from a to b of v of t dt. Right, and this feels like, wait, it's different, right? Doesn't it feel different where if I ask for average velocity position, you will give me this, you will give me slope, but then average velocity, given velocity, you would do average value theorem. Right, but I want to prove to you that these are the same things, because what's the integral of a to b from of velocity?
X of b minus x of a.
X of b minus x of a divided by what?
B.
B minus a, right? It's the same thing. It's just that depending on where you're coming from, if you're coming from the position standpoint, it's just slope. But if you're coming from the velocity standpoint, you got to take the antiderivative of velocity, then divide by b minus a. But they both reach the same point, just at a different startings. But it's nice to see that connection, right? That, oh, wait, we're actually doing the same thing. We're just coming at it from a different starting point.
So like if you have an acceleration function, you can still find the average
Velocity if you do the integral of acceleration. But you can also find average acceleration using the slope of velocity as well. Okay. Everybody goes here. Okay, so yeah, we'll do more of these, but hopefully we feel like this is a easy process, right? But we'll definitely get more practice. Okay, let's do a full particle motion problem here. This is very similar to what your test could look like, but from an integral standpoint. Page 6. Okay, we're going to need our calculator for this. Graphing calculator is preferred, but you can kind of still work around the issue of not having a graphing calculator with 36 Pro. But here, an object moves along a horizontal line. Your velocity is given. We're going to graph the velocity function, and we're going to pull from the velocity function like as if it was a derivative function. Okay, so let's go to y equals in your calculator. Make sure your mode you're in radian mode. Let's go ahead and type in your velocity function. So under y equals, you're going to type in 4 sine of, and then always use variable t, sorry, x, right? Don't try to match the variable in the problem. Calculator is always going to be in terms of x. Now notice that I have the indication as to how to set the window here, but I do want to kind of show you that that eventually we need to be able to set the windows ourselves. So go ahead and do zoom. If you do zoom 6, it'll go to a -10 by 10 window where all your x and y axis will extend to -10 and +10. So you see that. Zoom 6 standard. Let's see what the graph looks like. So this is going from 0 to 4. So all this mess is not going to be part of our graph, but it's nice to be able to zoom in on the parts that you want to look at. So here's a way that you can do it. If you do zoom box, you see that zoom 1, zoom box. Okay. Let me just kind of show you what we're going to do here before we actually do it. So what we're going to do is once you hit zoom box, you're going to scroll your cursor to the upper corner of where you want your box to be. And then you're going to hit enter. When you enter, this point will lock in, and then you're just going to move the box width sideways until you reach a point where you feel like you want to stop, and then you don't hit enter or anything, just hit down. And when you hit down, the box will begin to form, and then just drag it all the way down until you feel like you have the window that you want to look at. Hit enter again, and then it'll zoom in on just that portion. Okay. So zoom box. So right now I have my cursor kind of sitting in the upper corner of where I want my box to be. Hit enter. Sorry, thank you. My cursor is right here in the upper corner here. Hit enter once, and then you should be able to start dragging the side length of your box over. Don't hit enter again, just go down. And then you're going to see the box form. Hit enter again, and it's going to zoom in on just the parts that you care about. So between 0 and 4, it says find the times when the object is motionless. Well, if you're looking at your velocity graph here, then velocity motionless will be velocity 0. So velocity 0 will be at this point, and this point. All right, so we're going to scroll and try to figure out what those decimal values are. So the way you're going to get to those decimal values, you're going to do second trace, and then we're going to look for a 0. Okay, second trace 0. Let me write that down. Okay, second trace 0. I'm going to scroll to a point to the left of my first x-intercept. Hit enter. Then I'm going to scroll over to a point on the other side of my x-intercept, hit enter. And then I'm going to hit enter a third time, and it's going to find my x-intercept for me. So again, when you do second trace 0, you're going to scroll to this point, hit enter. So the calculator knows, okay, I'm going to start at this point, and then scroll to another point on the other side of the x-intercept, hit enter again. And now the calculator knows, okay, you want me to look for an x-intercept between the two boundaries that you just set for me, and it's gonna go and look for that x-intercept for you. You're gonna see the word guess question mark. That just means, okay, it's ready for you to ask the calculator, hit enter a third time, and it's gonna find that x-intercept for you. So we should get 2.46463. And you'll repeat that process again for your other x-intercepts. Okay, let me come around and see if you have any trouble. Okay.
Yeah, I don't think.
So here you're gonna scroll
So
up,
zero.
highlight this one. You see three x-intercept. So that's fine. The first one. That's a try. Second type again. 0. If you take it out, I'm gonna pick up to the left. He said right now, like, other side, like your adjective just to it was fine. I think that was, I think, you're trying to get some, let's say, to grasp it. Times the value. 3.9, that process.
I'd ask him if I can say, for my kernel.
Oh, wait, 3.0, 3.9. Like, what?
Kernel.
Yeah, you may need to wait a little bit more, so I'm gonna go to window.
What's this? So you switch that word to like 6 or something. That's like a window. So that's all production.
So you got 3.9.
Well, I got 3.4. 3.9. That's not this. Okay, so then I can just, it's really easy to check the second phase. It's like. Sign can't get.
Or because we're here.
And I guess that's where.
Thanks.
You use it, yeah. Hit enter, like, that is right. There it is.
Anybody have any questions about finding the x-intercept?
That's something.
So here's my sign line here. And these are my x-intercepts. And then my graph starts above the x-axis, so I know that initially it's gonna start moving to the right. It's gonna stop at 2.463. It's gonna move to the left. 3 seconds in, it's going to stop, turn around, move to the right. 3.9 seconds in, it's gonna stop and move to the left. So find the times when the object is motionless. We can just say at t equals 2.463. Okay. When does the object change direction between 0 and 4? So the sign changes confirm that not only are these places when velocity is 0, these are also places when velocity changes signs.
Do I have to have a because statement or?
Yes, I'm actually for because statement. Just say simply because v of t change signs. Yeah. Make sure you don't just say sign change, that you're actually naming what's actually changing signs. In this case, it's velocity.
Okay.
Part C, find the velocity at 3 seconds. So you can just plug 3 into the velocity function. I have my velocity stored under y1, so you can just do second trace, y1, parentheses 3. Okay, provide your units of measure as well. Acceleration is the what of velocity? Derivative, yeah. So I can just make my calculator do the derivative feature. So we do math 8. Math 8 will take you to your derivative feature. Put the velocity, put in the velocity function and then plug in 3 to figure out the accelerated, make the calculator find the derivative for you. And plug in the value. Okay, your units of measure is meters per second or meters per second squared. Okay, is the speed increasing or decreasing at t equals 3 seconds? How do we determine increasing, decreasing speed? Compare signs, right? What does that tell us? Decreasing because, yeah, different signs, right? Speed is decreasing. Displacement. So displacement is just x of b minus x of a, which is the same thing as the different integral from 0 to 4 of v of t. Right? If I can do this, then isn't this the same thing as x of 4 minus x of 0? It is, right? But I can just make the calculator do this calculation for me. Depth integral from 0 to 4 of my velocity function. So math 9. Total distance is just the what of displacement. Absolute value, right? So make sure you put the absolute value around just the v of t. Don't put it outside the integral. So show me your integral notation and then also be able to plug into the calculator. So you'll do math 9 again. But you do need to call the absolute value notation. So to find absolute value on the board there, math number ABS. It may take a second here, but it will get there.
Wait for E. I remember like unit 5, you said like check the sign of the acceleration function only.
Right, that is if the wording says, is the object's velocity increasing or decreasing? Then we just look at acceleration, but this is speed increasing, decreasing, so we gotta look at both signs.
Oh,
Yeah, that's the distinction.
Yeah,
You guys get 12.177 or 12.178, either is fine. Okay, part H, find the time when the object reaches minimum velocity. So this is the velocity function. So the minimum velocity is just going to be the lowest point in that interval, right? So it's going to be that point. So I just have to, what you're going to do is you're going to do second trace minimum. Okay, you're going to trace second trace minimum. And when you do second trace minimum, this is what you're going to do. You're going to use your cursor and you're going to scroll to a point to the left of the relative minimum, and you're going to target that point there. And then scroll over to the other side of your relative minimum, hit enter again. And now you should have two boundaries for the calculator to look for the relative minimum. Okay, what you don't want to do is you don't want to put the cursor right at the minimum, because then the calculator has no way of knowing your left and right bounds. So don't try to do the calculator's job. Let the calculator find that relative minimum for you. Okay, so give it a nice, easy boundary so that you can look for that relative minimum. And the same thing, right? If you're looking for relative maximum, pick points on either side of your relative max, and the calculator will look for that hill somewhere along your interval. Okay, so second trace minimum, or second trace minimum, that's option 3 there. So the minimum is -4 at 2.926 seconds. So both of them will be helpful because it says find the time when it reaches the minimum velocity, that's 2.962, and then also the absolute minimum in that interval is -4. So
Wait, are H and I asking for two different things or?
yeah, H is asking for the t value, and I is asking for the velocity, so it's the y value, right? Okay, given x of 0, find x of 4. So this is first theorem. Oh, sorry, guys. So given their starting position, find your ending position. So we know this is really a rearranging of first theorem, but in a form that is helpful for particle motion. If I want to find out where I'm going to end up, I'm going to have to need where I'm going to start, plus how much progress I made in that time interval, and that's going to give me my ending position. Okay, this is a calculator entry, but we already found this, right? We already know the displacement in that 4 seconds is 7.753. So if we're starting at location 2, and if we move to the right 7.753 seconds, we're going to end up at position 9.9753. Part K, find the average velocity. So we have velocity function. Let's do average value theorem. We already know this value, right? 7.753 divided by 4, 1.938. So across all the velocity between 0 and 4, the average is going to come out to be a 1.938. So now part I is just asking, okay, we know this velocity, we know this particle is going to reach this average velocity, guaranteed, right? I can't have an average velocity and that particle not reach that value at least once. So if I want to find out when the object reaches velocity, I can set velocity equal to 1.938. Okay, so there's two options, but I'm going to tell you that for me, the second option is going to work a little better. One thing you can do is you can graph your velocity function. Okay. You can graph 1.938. And then just simply look for those intersections with your calculator. The other option is, why don't we do this? Why don't we do v of t minus 1.938? Graph this function. Because whenever this graph hits the x-axis, that's the solution that we're looking for, right? So if I graph this function instead, then I can just simply look for my x-intercepts, and my x-intercepts will just be a t-value that will make this statement true, which is where v of t is equal to 9.938. Okay. So my strategy there is I'm going to sketch another graph and call it 4 sine of.
You can't do y1 with then y2 or.
Oh, yeah, I could. Yeah, actually, you know what? This is better. I could just call y1. That way I don't have to go back down. That's good. Yeah. So second trace y1. Let's just do y1 minus 1.938. But I don't want to see the first graph. So if you have multiple graphs and you don't want to have to erase it because you might need it later. You see that equals, you see how the equal sign is highlighted? It's got that black mark around it. If I scroll over the equal sign, hit enter, that will make that equal sign. It'll unselect that equal sign, which means it'll still remain in the calculator, but it won't show up on the graph. So you don't see to look at all these different graphs. So I just do my velocity minus 1.938. I'm just going to hit graph. If I can simply look for the x-intercept, then that is my solution where my velocity graph will hit 1.938. So if I scroll to these points here, I get 2.279, 3.406, and 3.814 using the second trace 0 option. Okay, so we're going to start the next unit tomorrow, but I think the lesson won't be that long where I can still use the last 10, 15 minutes just to do one of these types, right? So you'll see a particle motion like this. You'll see a derivative graph that we did at the beginning of class, and then you'll see a Riemann sums. Okay. But a few minutes left. Why don't we see if we can make some progress with the next page? Previous page, page 3. And let's do another 5 minutes of derivative graph. Okay, page 3. It's asking for G of 2, G prime, and G double prime. Let's just go ahead and get all the relationships in front of us, right? If G of X is the integral of f of t, then G prime is simply the derivative of this, and that's second theorem, which is just f of x. And G double prime is simply f prime, right? So you're always going to have this relationship here where G and F are staggered. So G prime is F, this is F. So basically we're looking at a G prime graph here. And if I want to find G of 2, I just look at my definition and add and total the area. If I want to find G prime, I can just look at the order pair. If I want to find G double prime, then it's simply the slope of my F graph. Again, if it helps, you may want to kind of lightly shade in what you're working with because you're only looking at the shapes between the graph and the x-axis. Any other shapes is not part of our problem. Okay, you got a triangle, a semicircle, and then there's another triangle. Okay, I'm going to just label what those values are. 1/2 pi r squared. My area is going to be -2 pi, but I'm going to split it up into negative pi and negative pi here. So G of 2, just follow what the rule says from -2 to 2. So from -2 to 2, I see both my regions are below the x-axis. Those are negatives there. So negative pi is -2 pi. G of -4. It feels out of order, but go ahead and write it where it is telling us to write it. And if you want to flip the bounds to make it easier to interpret, you can, since this is going backwards. So I need to pull a negative in front. So -4 to -2 that's -1, but then there's a negative that's already been pulled out. So negative over -1 is +1. G of 6 can be the entire interval here. So -2 pi. Oh, sorry, from -2 to 6. Sorry, just that region there. -2 pi plus -2 pi plus 4. G prime of 4. G prime of 4 is this order pair, right? G prime 4 is f of 4. And f of 4 is simply the y value there, so 2. G prime of -2 is just f of -2. F of -2 is 0. G double prime of 5 is just f prime of 5. F prime of 5 is asking for the slope of the f graph at 5. That slope there, just had to figure out the slope of this line. So I'll pick 2 points that I can find. Down 2 over 2. That's the slope of -1. Okay, you're looking at your derivative graph. So anything above is positive slope, anything below is negative slope. And then we answer these questions based off our slope sine line. For I, create your second derivative concavity sine line. And then for J, we'll do EBT, where we're pulling endpoints and critical points into our G of X function, and then just locating, comparing the Y values. Okay, so we'll start the next unit, but I think we can always do like 15 minutes of review Tuesday and Wednesday, and then by Thursday you should feel really good if you don't already feel good about these 3 problems. Okay, all right, can we get your phones?
Yeah, the quiz, you have to know part of the devices. You have to know like the internet.